In the acid-base unit on the AP exam, we come across what is quite possibly one of the hardest mathematical concepts for the AP exam, buffers. And this mainly has to do with how you learn it. Your textbook goes into a very long, drawn-out explanation of what's called the Henderson-Hasselbalch, some guy's explanation of how to calculate buffers and changes in pH. However, NIMSY gives us a much easier, much simpler explanation of how to calculate buffers. And that's what we're going to work on today. First off, you need to know that a buffer is a solution of a weak acid or base and its conjugate salt. And together, the weak acid or base and the salt resist changes in pH. So these problems often read as something something ic acid and something group 1 metal 8 are mixed. Because remember, all group 1 metals are soluble. So anytime you see those combinations of words, something ic acid and some group 1 metal 8 are mixed in solution, you've entered the land of buffers. And most of your other test takers will begin to cry and weep, but you will think of Halo, and you will think of the example I'm about to give you. As many of you have probably guessed, I, Coach L, have no life. And I leave here in the afternoons, and I go home, and after going to the gym, I meet an old college buddy of mine, and we get online, and we play Halo, where you play as this guy, the Master Chief. And you are invading this thing called Halo. You're invading this ring, and there's a bunch of aliens on it that want to kill you or stop you from taking over their ring. One type of alien is called a grunt, and they look like this. They come in a bunch of different forms, and they're usually very easy to kill. They're rather weak. However, while you might be focusing on stronger enemies and taking them out, these grunts are sneaky. And if you get too close to one of them, or you shoot it just a couple of times, they can go kamikaze, and while you're doing a great job taking out their much stronger, much more difficult companions, they can strap a bunch of grenades to them, run at you, and take you out. And this leaves you usually cursing at your friend, going, I have no idea how I just died. I just exploded for no reason. And it's because these little guys go kamikaze on your hiney and take you out. This is a lot like how a buffer works. A buffer is a weak acid, so say, or weak acid or base. So let's say you have acetic acid, and it's salt. So we could have acetic acid and sodium acetate. And in solution, these two will go back and forth, becoming either an acid or a salt, establishing that equilibrium. And all is peaceful in their ring until an invader comes along. Once that invader comes in, these weak acids and bases these weak acids and their salts have no chance of fighting it off hand to hand because they're not strong like it. But they can go kamikaze, strap a bunch of grenades to them, and jump on that strong acid or base and neutralize it. Because if I add a strong acid, there's a base component that can jump on and neutralize it. If I add a strong base, there's an acidic component that can neutralize it. So really, buffers are just a common ion effect that resist changes in pH by neutralizing strong acids or strong bases as they dissociate. There is only one formula you need to know in order to do acids and bases and buffers this way. However, it is not on your formula sheet, but it's something worth so many points, both on free response and multiple choice, that I implore you to please know this formula. And it is extremely easy. The concentration of hydrogen ions equals Ka times the ratio of the concentration of acids to the concentration of bases. And in both cases, it will be a weak acid and a weak base. So if we're asked to calculate the pH of 0.5 liters of buffer solution that's composed of 0.5 molar formic acid and 0.7 molar sodium formate, we can do that. The second part I'll talk about in just a moment. So for the first part, calculate the pH of 0.5 molar and 0.75 molar sodium formate. First off, you need to know that you don't need to know. You need to know that you don't need to know any Kas. They'll always be given to you, and if they're not, then you're going to have to solve for them. So I'm going to give you this. This is a Ka that I pulled off the internet. The Ka of formic acid is 1.8 times 10 to the minus fourth. Now using that, we can use our formula. Concentration of hydrogen equals Ka times concentration of acid over the concentration of base. So our acid is formic acid, sodium formate. Typically anything group 1 metal ending in ate or ite is going to be our base. At least if we know what the acid is, then the other one must be the base. So we should be able to calculate the concentration of hydrogen. So we plug in our Ka value. Let's plug in our concentration of acid. We can plug in our concentration of base. And then we just pull up a calculator. Since we know that, we can then say, therefore, the pH is 3.89. Does that make relative sense to our Ka? 1.8 times 10 to the minus 4. 3.89 is pretty close, or around in the neighborhood of 4. So yeah, I would say that makes pretty good sense. All right, the second part of this question says, now we're going to add an invader. So this is the pH before we added anything, but now we're going to add 10 milliliters of 1 molar HCl, a strong acid. So if we're going to add an acid, we're going to increase this number on top, but the bases are going to come to their rescue and neutralize some of it. So we're going to add to the acids and subtract from the bases, because some of the base is going to get used up in that neutralization. So we're going to keep the same general format, but now we need to add to this. Now when you do these adding and subtractings, don't stay in molarity. Don't stay in concentration. Change instead to moles. So let's figure out how many moles of each one of these we have. So hopefully you remember they go from molarity to moles, you multiply by liters. But look at this, my liters aren't the same. I have liters here, I have milliliters. Let's convert this liters to milliliters and we'll work in millimoles. Yes, a millimole is a millionth of a mole. Thousandth of a mole. So 0.5 liters, that is 500 milliliters. So 0.5 times 500, this isn't 0.5 molar, this is now 250 millimoles. And 0.7 times 500, this is 350 millimoles. Alright, and let's look at this. We're adding and subtracting how many moles of the strong acid or strong base. Let's see, we've got 10 milliliters, so 10 times 1 is 10 millimoles. Now it's an acid, so we're going to add that 10 millimoles to the acid side and subtract it from the base side. Alright, once we do that, we end up with 260 millimoles over 340 millimoles. Multiply all that out and we find that the concentration of hydrogen equals 1.38 times 10 to the minus 4. Therefore, the pH equals 3.86. Does that make sense? We added an acid and the pH decreased. I'd say that makes some pretty good sense. So in this case, we were given Ka. If you're not given Ka, say they gave us Kb, say we were talking about a base here, so some base and its conjugate salt, we would be given a Kb. If you don't get a Ka, find a Ka. So remember, Kw equals Ka times Kb. Another type of problem that you'll be asked to do is to prepare, or how would you prepare a buffer solution? So you need to realize that the concentration of hydrogen is equal to the Ka times the concentration of acid over base. And if the concentration of acid is equal to the concentration of base, so basically this is 1 to 1, then this goes away. And when the moles of acid equals the moles of base, concentration of hydrogen equals the Ka, or the pH equals the pKa. So anytime you're asked to construct a buffer, you're going to use an acid and conjugate base, or base and conjugate acid, whose Ka values have an exponent that's close to the desired pH, and then use equal concentrations. Or determine the ratio of acid to base, and then use concentrations that allow for an easy mixing. So when preparing buffers, you should use concentrations that are dilute, so between 0.1 molar and 1 molar. Don't get anything too concentrated. And you should use a situation in which your pKa, so the negative log of your Ka, is approximately equal to the negative log of your concentration of hydrogens. Your pKa approximately equal to your pH. So if we're asked to calculate the ratio of conjugate acid to base, you will need to use the same formula that we've had before, but Ka is going to have to be given to you. So I've already done that for you. Ka for acetic acid is 1.8 times 10 to the negative fifth. So if we want to have a pH of 5, that means that the concentration, you need to zero in on that and say, well, the concentration of hydrogens then must be 10 to the negative 5. So if we want to keep our concentration of 10 to the negative 5, and we know what Ka is, we're asking what is the ratio of acid to base. If it asks for the ratio of base to acid, we would just take the reciprocal. But since we have this here, we can automatically do it as is. So we're trying to get a concentration of 10 to the minus 5. We know that Ka is 1.8 times 10 to the minus 5. And we're solving for this ratio. So concentration of hydrogen divided by 1.8 times 10 to the minus 5. 10 to the minus 5 cancels, and we're left with 1 to 1.8 as our ratio to acid to base. And then it asks how we would make this solution. So we would mix 1 mole of acetic acid with 1.8 moles of acetate in enough water to dissolve the salt. And you do have to put that, enough water to dissolve the salt, because if you don't, you can't just say I'm going to mix 1 mole. I'm going to mix 1 mole with 0.8 moles, because you need to point out this is wet chemistry and has to be dissolved. You do not, however, have to specify the amount of water, because that's not crucial, because the amount of water is going to be the same for both of them, so the total volume is going to be the same.